Hey physics students, hope you guys are doing well. I'm going to be doing a lab activity with you guys today on circuitry, and we try to make this fun, and we use some Play-Doh and some lights and some modeling clay so that you understand how electrons flow through wires and conduct electricity, because it's sort of like cars on a street. The cars have to drive on the road, and the roads really are going to control how those electrons or those cars are going to act like electrons on the wires, or a road and a car driving on a road. And sometimes there's things like one-way streets, sometimes there's shortcuts, and sometimes there are multiple lanes and highways. All of those things apply with electricity. And just think of the cars like electrons that are negatively charged, and they're just little negative electron dots moving like cars. And instead of a road, it is a wire. The reason we're doing this is because the last unit of physics is really focusing on solar photovoltaics. And so solar photovoltaics is the solar panels that you see on houses that are used to produce electricity. And that's an amazing alternative energy source because the sun is free. And if you have those solar panels, you're not worried about things like PG&E shutting the power out. You can go remote living. You can have those solar panels up on your house to give you electricity when you want it. And then when the sun's not shining, you typically put batteries as a backup to get the power at night or during the rainy seasons. So let's go ahead and get started. I'm going to switch this around to show you my notebook so you guys can just follow along with me. Okay, students, so this is the first page of your notebook. As you can see, we've got a daily learning objective. Anything that is starred in these notes that I'm going to be sharing with you on a Google Doc, I would like you to write down, and that's how you're going to get your points for today. I want you to just copy down anything that's starred or highlighted in your notes and process the information along with me. So I'm going to just hold your hand through this whole thing so it's not too overwhelming. So our daily learning objective for today is to understand the difference between conducting and insulating materials. That's actually a review for you guys. We already did conductors and insulators in our electricity and magnetism labs, but we'll relearn that subject today. Second is to demonstrate how to build a closed circuit while avoiding short or open circuits. And the third learning objective for the day is to understand how a circuit can convert electrical energy into light energy. So go ahead and write those learning objectives down now. Okay, so I've already gone over the background for you guys. So let's just go ahead and jump into the LED definition. Please write down this definition. LEDs are tiny lights found in many electronic devices. Point out some LEDs. So LEDs are things like, I'm not in the classroom right now, but these are little LEDs, and here's a bunch of LEDs right here. And you typically see these in any sort of electronic device that has really small lights that light up. Usually they'll be like green light, little tiny light goes on, you know that it's working. Red light, maybe it's off, it's not functioning properly. Those are LEDs. So the other thing about LEDs is that they are directional, and they're only going to light up when electricity flows through them in a proper direction. So if your LED light is not working, like today when we go through the lab, if the light doesn't light, it doesn't mean electricity is not going into it and trying to attempt to reach it. It might be that you just need to flip the direction of the LED, and we'll walk through that today and you'll see what I mean. But it's sort of like LEDs are one-way streets. The electrons can only enter in through one side and exit through the other side. You can't put the cars traveling in the opposite direction. The light won't light up if the electrons don't go in that one direction way, and that's what we're trying to say here. Now, conductors versus insulators. I would expect you guys already remember this from our electricity and magnetism labs. Conductors are materials that let electricity flow through them easily. And as you know, metals are good conductors, and we've gone through that already. Insulators are materials that block electricity from flowing through them, like plastic, rubber, wood, our styrofoam, our big air bubble stuff that we did in our electricity and magnetism labs. So should be a review for you, okay? Conductors basically have some sort of a charge carrying possibility, and they allow those negative electrons, which we call electricity when they move, to flow through them properly. Insulators, you know, they should have those air gaps that we talked about a while back, and then that is not allowing the electrons to flow through them. And so those stop or prevent either energy or electron flow, and those are called insulators. Okay guys, so one other thing you want to add to your conductors versus insulator is which for our dough type today. So Play-Doh, and you know what, if you guys have some of this stuff at home, you can try it. Play-Doh is a conductor. It just means it's got a lot of salt. You know, the salt that you add to your food. That's an ionic compound called salt, and it carries a lot of charge and allows electrons to flow through the substance. So it's a conductor. So today, our material that is a conductor is going to be Play-Doh. And the insulator for today is going to be modeling clay. So modeling clay does not have salt inside of it. It does not carry a charge and does not allow electricity to flow through it. Almost like the air gaps and the styrofoam we did in our electricity and magnetism labs. So we're going to use this as an insulator. So add that down in your notes. And so today we're going to just follow along with the worksheet, and I'm going to help you guys just write out the answers for you so that you guys can see how to do that. What you see right here is that we have two of the conducting doughs, the Play-Dohs. These are both Play-Dohs. And I have what we call a squishy circuit, which is basically just a bunch of batteries, like AA batteries or AAA batteries, connected to two wires. And so electrons are coming off the batteries, and those negative electrons are just flowing through the wire, okay? And that's causing what we call a circuit. And so we're going to play around with that today to get some specific definitions. Let me go ahead and switch this around to show you your worksheets. Okay, so this is the next sheets that you're going to be working on filling out. We already did the top where we conducted the battery and the wires into the conducting dough, which is Play-Doh. Also, we talked about how LEDs are like one-way streets. That is the word polarity. And so today, one of the things we're going to do is whenever I use an LED light, I need to make sure that I put it in a specific direction. If I don't put it in a direction, then the electrons can't flow through the wire and light the light bulb at the right way. So please copy this down. The longer leg of the LED must always connect to the red side of the wire because LEDs have polarity to them, and polarity means that the electricity can only flow in one direction. The electrons that are negative only will move one way, like a one-way street. So if your light is not lighting, and I'm going to show you this in a second, it means that you're just putting it in the wrong way. So long goes to the red wire, okay? So we're going to go ahead then and start doing this part where we will just follow the directions. I do want you to write to, as I go over these definitions like open circuit, closed circuit, I not only want you to take those definitions on this second page, but then put them on this worksheet right here. So our goal today is going to be defining what is an open circuit, what is a closed circuit, which was on that page I just flipped, what's a short circuit, and then going through how we use the conductive Play-Doh versus the insulating clay. And so some of these answers right here will also be behind on the following page worksheet. It's sort of out of order a little bit. And so these definitions for short circuit and how we use the clay and the Play-Doh will be used to fill out these last two parts of the worksheets in case you don't get it as I go through it. So let's go ahead and get started. All right, so first thing I want to show you guys is the polarity part of the LED. As you can see, there's two legs on this LED, and all LEDs have two legs on them. And one is longer and one is shorter. And so it's really small difference here, but you can see that this side right here is longer than this side over here. And so what we do is we want to make sure that that longer side, as you already saw in your notes, goes where the red wire is. So it always, long side goes with the red wire. What happens if I flip it? The light doesn't light up. And that doesn't light up because I'm trying to push electrons through something that's like, nope, one-way street, can't go through this way. So that's what we're saying about polarity. In order for the electrons to flow, they have to be going in that exact direction so that the electrons can flow through and keep going through the circuit. Okay, so that's the first part on polarity and LED lights. All right, I'm going to go in order of the worksheet, and when I take this and I have it not connected, it's almost like having an open door or a closed door. When the electrons are coming off the battery, they're going through the wire into the red Play-Doh, and then they're trying to go up this side and go through the other leg. And then if you were to connect it into this Play-Doh, they would go up this wire and then go back into the circuit, the battery, and then just keep circling round and round and round like a street, and the cars are running like in a circle. But because the door is open, this is, see this little leg, it's open versus closed. If I shove it into the Play-Doh, we call that a closed circuit. If I open it, like an open door, then the electrons don't have a road. There's no path. So the electrons cannot keep going through and go round and round and round. So this is the first definition. We have an open circuit, means that the circuit is not connected. Open door, no connection, electrons have no way to keep going around in the circle, okay? Closed circuit, we have a closed circle. Circle current circuit is what I say, CCC, circle current circuit. When you have it all fully connected and then the door is closed, the electrons now have a path to travel round and round, and we have this circle and they just keep moving, okay? So let's go through the worksheet now and fill that out. All right, so we're on this page where it just says, turn the battery pack switch on, but do not connect. That's what I just did. So the leg is not connected to the Play-Doh. What is that called? That's called an open circuit. There's no complete path for the electrons to flow. So let's go ahead and add that definition here to the drawing. Okay, you guys could just sketch this if you don't want to print it or whatever. So open circuit means that there is no path connected, like wire is cut or not touching, for electrons to flow on. Okay, and so what would we see? We would see in an open circuit no light. Okay, so there you go. Now the next one is closed circuit. That's like a closed door. So we now put the leg in, closing the circuit, circle current circuit. The definition is we have it lighting up, and that's because there's a complete path for the electrons to flow on, the electricity to flow on. So the definition here would be closed path And actually, we probably should go back up here and not say no path, but like an open, either no path or an open path. Like it's either cut or it's just not fully closed or connected. So closed circuit, closed path for the electrons or electricity to flow on. So I say this is a circle. Current. Current means the electrons are flowing like a water current in a river. And that's what we call a good circuit. A circuit means that it is closed. So lights up in a closed circuit. And you see the nice pictures also demonstrate what we're talking about in our definitions here. All right, now we're going to move on to what is a short circuit. All right, guys, so what's a short circuit? Short circuit is sort of like a shortcut, right? You're going along a road, you're in a car, and you're like, oh my gosh, there's a traffic backup. I need to get there quicker. What other road that most of the visitors don't know about can I cut across? Because I want to still get there quicker. It's the path of least resistance, and that's what electrons do. If you have this closed circuit and you've got the electrons flowing in this circle and the circle is going around, the whole point is to get that light bulb to light up, right? So we want the electrons to go through from the battery, through the wire, up in this part of the leg, go up, light the light bulb, go down through this metal leg, then go through this blue Play-Doh, then go up the black wire and back again. But if for some reason you create another shortcut option for the electrons to go, they're going to do it. Just like if you open up a shortcut and there's a backup of traffic, people are going to go cut across. So here's where we have that, and that's what you're going to see. As soon as I touch the Play-Doh, what happens is that the electrons are no longer forced to go through the long way through the light bulb. They're actually cutting across right here. The electrons are going through the red dough, and then because these are touching, they're jumping straight off into the green because it's a shorter path, a shortcut, short circuit, and then it goes up. So sometimes in electricity, if the lights go out and you're trying to figure out, is there faulty wiring? Sometimes it could be that there's a short circuit, that somehow the wires are crossed and the electrons are going to go through that shortest route possible. Now, when I open it up, bam, they're forced back to go through the long road, but also through the light bulb. It's really important with electricity and wiring that you don't create short circuits. You want the electrons to go through your devices. You want them to light up when you want them to light up. You don't want them just choosing random places. And also, you don't want any sort of electrical fires and such from crossing over wires. So that's not good either. Okay, so we're back on our worksheet now. Now this was just right behind the main worksheet we're filling out, just in case you can't find it. So we're going to add this short circuit definition to the worksheet and then describe what we just saw. So when we have the lumps of clay touch, that creates the short circuit where the electrons just skip going through the light bulb. They decide, I'm just going to go through that shortcut of the clay because they're touching. So we just created a shortcut. The definition of a shortcut is that electricity likes to flow the path of least resistance. When the lumps of Play-Doh touch, the electricity takes a shortcut through the Play-Doh instead of going through the LED light, so the light does not light up. So we're going to go ahead and just add that right here on the bottom. So shortcut, what did we see? No light. And that's, you can sort of, right there, that's our shortcut. It's like, boom. Going here, oops, wrong way. That's what happens when you try to videotape yourself. This way, not. So not here, shortcut. So it's going through the clay like this way and not, let me get a different color. It's not going this way anymore. It's not going through the light. It's now going just through the clay and back to the battery. So it's what we call a shortcut. All right, so let's go ahead and write that down. Shortcut is a short circuit electrons or electricity will flow through the path of least resistance. If there is a shorter way, then the electrons will take the shortcut, and we call this a short circuit. Okay, so there you go. Make sure you guys getting all this down. Okay guys, what we're going to do now is we're going to start using the conductor versus insulator materials to try to make the shortcuts not occur. And so what we're going to do is we're going to take the modeling clay. Remember, modeling clay was an insulator, does not allow electrons to flow. Okay, it's almost like the coating of the wire, the black and the red are like a plastic, and they have the ability to stop the electrons from flowing. We call those insulators. Then we have the charged Play-Doh, which can carry and conduct electricity through it. So right now we've got it set up perfect, where it's a closed circuit. There's no short circuit going on, but we know that if we touch it, bam, it's going to go out. And so as we get into the next labs and activities, we're going to build more intricate circuits, and we don't want this to keep happening. This is no good. So we're going to actually try to put the insulative clay in between, and we're going to do that just to make sure that we don't have any of those short circuits. So we're going to draw on our knowledge of what's a conductor, the Play-Doh with the salts, what's the insulator, the yellow clay, because it doesn't allow the charge to flow. And those properties are going to be utilized from now on in order to make better circuits. So let's go ahead and write that up. Okay, we're back where it said short circuit up here. We're now going on to how do we prevent short circuits, okay? Preventing short circuits is as simple as just insulate, insulate, insulate. You know, you want to put your wires, you want to make sure that they're coated so that the electrons just don't flow wherever they want. Plus, that could be a fire hazard. So here's our answer, and we're going to write that in our worksheet. We can use insulating dough, which is clay, to separate the two lumps of conductive dough or Play-Doh. And prevent them from touching. This will help prevent short circuits. So that's what we did. This allows a closed circuit to occur with nice insulating clay in the middle. And then these are our conductors. Oh, they already had it labeled. Sorry, guys. Okay, go ahead and turn over, and we're going to fill out that worksheet now. So define conductive Play-Doh versus insulating clay, and how are we using both here. And so the clay does not conduct electricity or allow electrons to flow because it is a insulator. Okay, and that's clay. And we put that here. Then Play-Doh does conduct electricity and allow electrons to flow. And so we put those on the edges here and here on the outside. So we put the insulator in the middle to prevent short circuits. Any other observations about the circuit that we... Okay, I spoke too soon. We still have some post-lab questions. Real quick though, let me go over the careers with you guys. So we will be doing these post-lab questions in a second, but I do want to go over, as always, the CTE class talks about different options for your future. One of the things we're really dealing with here, if you like dealing with wiring and electricity and lights, that would be a career of an electrician or an electrical engineer. So if you're interested in that, maybe read up on this, okay? Those are definitely good paying jobs in the future that relate to electricity. This is what's coming up next. We're going to get into parallel versus series circuitry with using these circuits. They're a lot easier to see. And last, post-lab questions. So, how could we tell if our circuit was connected successfully? It lights up. Basic. What are some problems we ran into when connecting our circuits? Shortcuts occurred when Play-Doh touched, creating a short circuit and no lights. So that all goes with that one. Sorry, guys. And then, can anyone describe how energy flows through our circuit? The battery produces electrons and flows through wire, then dough, then light, then dough, then back to wire and battery. And last, look around the classroom or around your room. Think about other rooms at home or school. Can we identify more examples of circuits where energy is converted from one form to another? I mean, computers are built with massive circuits, TVs, electronics, whatever, anything that's any electrical devices. The list goes on and on. Really, you guys could just write it up. All right, so that's it, guys. Hope you enjoyed this first section of squishy circuits and circuitry. And this is, remember, going towards our final goal of understanding how solar photovoltaics will work. And we will get there. This is just the beginning. Take care. Stay strong. Hope you guys are all doing well. Miss you.